Hi, I am Emily and welcome to this video on Java engineering, focusing on control flow, loops, and the core pillars of object architecture. This blueprint is standardized for Java 21 plus virtual machine execution, covering technical concepts from episodes 5 through 15. Our curriculum scope is divided into three key areas: control and logic, covering decisions and loops; blueprints and OOP, focusing on classes, objects, and memory management; and safety and hierarchy, which explores encapsulation and inheritance. Let's begin with part 1, flow control and logic structures. In this section, we provide a deep analysis of runtime instruction routing, logical evaluations, and advanced branch compression, starting with episode 5. Computer code execution typically flows line by line. However, conditional branches allow the CPU to diverge. The Java virtual machine uses specific jump instructions in bytecode to dynamically skip memory routines based on these conditions. A single branch "if" block executes its wrapped scope only if the controlling expression evaluates to true. It is considered best practice to always use curly braces in production to avoid scope-related bugs when adding further expressions. Moving to dual branch logic, the "if-else" structure introduces a mutual exclusion barrier, ensuring exactly one of the two branches executes. This effectively eliminates redundant code evaluations and optimizes instruction execution at the register level. In an if-else-if chain, execution proceeds sequentially. The first condition that returns true halts all remaining evaluations. Therefore, always place the most specific conditions at the top of your chain to prevent general checks from catching them first. The short circuit AND operator, or AND, optimizes logical products. It only evaluates the right side if the left side is true. This is vital for preventing runtime errors, such as null pointer exceptions, by performing safety checks first. Similarly, the short circuit OR operator performs a logical sum optimization. It immediately returns true if any term evaluates to true. For performance, you should place the most likely or fastest checking conditions first in your expression. When dealing with complex Boolean logic, remember the operator precedence chain. Unary negation happens first, followed by comparisons, then logical AND, and finally logical OR. Use parentheses to explicitly enforce clarity and prevent bugs. Legacy switch statements execute sequentially. Without a break statement, execution falls through into subsequent cases. This behavior is a common source of bugs, as it can unintentionally trigger code in adjacent blocks. Modern switch expressions, introduced in Java 14+, use arrow syntax to eliminate the risk of accidental fall-through. These expressions can yield values directly, work as returnable statements, and ensure all conditions are covered at compile time. We now move to part 2, code iteration mechanics. In this segment, we provide a comprehensive analysis of loop operations, various testing patterns, and their associated resource costs as covered in episode 7. Looping in the JVM is the repeated execution of machine instructions. High-level loops are translated into low-level register comparison operations, with the JVM converting loop structures into efficient backward offsets. The standard for loop offers a structured approach to control flow by keeping initialization, condition checking, and step modification in one line. It is ideal for scenarios where the exact iteration count is known, such as when traversing arrays. Next is the pretest while loop. This structure verifies its condition before executing the loop body. If the control variable is initially false, the loop body will not execute, which is useful for processing data streams of unknown length. In contrast, the post-test do-while loop ensures the loop body executes at least once because it checks the condition after execution. This is ideal for interactive user menus or retry routines that require an initial run. Sometimes you need to exit a loop early. The break statement halts the enclosing loop instantly and redirects control to the code immediately following the loop, which is efficient for search routines once a target is found. If you only need to skip a single iteration, use the "continue" command. This skips the remaining logic for the current iteration and jumps straight to the next update step, helping avoid deeply nested if blocks. Be mindful of performance when using nested loops. Nesting increases resource costs quadratically. Processing 10,000 items in a nested loop results in 100 million internal steps, which can create significant execution delays. Infinite loops occur when termination conditions never resolve to false, which can drain system resources. The Java compiler helps by identifying unreachable code, but always verify your loop variables are correctly modified on every pass. We are now transitioning into part 3, the object-oriented blueprint. This module focuses on shifting from simple procedural scripts to modular systems, utilizing class structures, and understanding heap memory dynamics. Procedural architectures separate state from logic, which can become hard to maintain. Object-Oriented Programming, or OOP, solves this by binding state and actions together, modeling real-world behaviors through encapsulated objects. A class serves as an abstract template. It defines what data an object can hold and what actions it can perform. Importantly, declaring a class does not allocate memory. It simply acts as the master structural blueprint. An object is a concrete instance of a class, created in memory using the new keyword. Each object maintains its own independent state variables while sharing the same class-level executable logic. Fields within a class define the internal state. When you declare these fields, the JVM automatically assigns standard defaults, such as 0 for numeric types, false for booleans, or null for object references. Methods provide the operational behavior for your objects. They contain logic that manipulates the object's internal state. Good method design involves validating inputs to protect object integrity. Understanding JVM memory is crucial. The stack holds local variables and method call frames, while the heap manages objects. This separation ensures efficient memory management and performance for complex applications. The this keyword is used to reference the current object instance. It is primarily used to disambiguate class fields from parameter names when they share the same identifier, ensuring code clarity. Finally, manage your memory safety carefully. Null references cause crashes if accessed, but the JVM's automated garbage collector cleans up objects with no active references, helping maintain a small memory footprint. We are now beginning Part 4, Object Construction Mechanics. In this segment, we will explore the lifecycle of an object, how constructors manage state initialization, and how we can use dependency assignment patterns to build robust code. A constructor is a specialized block of code that runs immediately after memory is allocated on the heap. Its primary job is to initialize an object's state, ensuring it is ready for use before any other logic interacts with it. If you don't define a constructor, the Java compiler automatically adds a public, no-argument version. However, this invisible default disappears the moment you write your own constructor, meaning you must define it manually if you still need it. Parameterized constructors allow you to inject initial values at the exact moment of creation. This guarantees that critical fields are populated with valid data, preventing common bugs related to uninitialized references. Constructor overloading allows you to define multiple initialization paths within the same class. Each must have a unique parameter list, giving users flexibility to instantiate objects based on the data they currently have available. To reduce code duplication, you can use constructor chaining with the this keyword. This allows one constructor to delegate setup work to another within the same class, provided the call is the very first statement in the body. Under the hood, object creation follows a three-step pipeline. The JVM loads and verifies the class, reserves memory on the heap with default values, and finally executes your custom constructor code to finalize the object state. Moving into Part 5, Information Hiding and Safety. Here, we discuss how to use access modifiers, getters, and setters to protect your object's internal state and enforce necessary class invariants. Encapsulation is the practice of bundling an object's state and methods while blocking direct access to internal variables. By hiding implementation details behind public interfaces, you ensure that external code cannot corrupt your object's integrity. Access modifiers define your boundaries. Private restricts access to the declaring class, ensuring complete internal control, while public exposes elements globally, acting as your formal contract with other system components. Between these are package private and protected scopes. Default visibility limits access to the current package, while the quote protected modifier grants access to subclass derivatives, even if they reside in different packages. Exposing fields directly is a dangerous practice. It allows external callers to bypass logic checks, potentially putting your system into invalid states that are extremely difficult to track down or refactor later in development. Getters and setters act as vital filters. By forcing external code through these methods, you gain the ability to intercept read requests and validate any writes, keeping your internal state consistent and secure. To design truly immutable objects, omit setters entirely and declare all fields as quote private final. Once created, these objects cannot change, making them inherently thread-safe and safe to share across your application without extra locking. We conclude this overview with a look at Part 6, Object Inheritance Hierarchies. We will examine how the extends keyword and method overrides allow us to build scalable, reusable models and resolve dynamic method lookups.